Previously, we showed that the thermodynamic properties of some pure substances can be found in property tables. A more practical and desirable approach is to have equations which provide relationships between properties. Such equations are called equations of state. The simplest and best known equation of state is the ideal gas equation, which provides the following relation between pressure, volume, mass, and temperature of gases. The constant of proportionality between these properties is called the gas constant, R. This constant is different for every gas. An ideal gas is an imaginary substance which obeys this relationship. It has been experimentally observed that real gases approximately obey this relationship at low pressures and high temperatures. Deviation of real gases from ideal gas behavior can be measured using the compressibility factor, Z. The closer the compressibility factor is to 1, the closer the gas approximates the behavior of an ideal gas. The compressibility factor for any gas at a given state can be found in the generalized compressibility chart as a function of the reduced pressure, PR, and the reduced temperature, TR. The reduced pressure is the actual pressure of the gas divided by the critical pressure, and the reduced temperature is the actual temperature of the gas divided by the critical temperature. We will now learn how to determine changes in internal energy and enthalpy of ideal gases. Recall that the specific heat at constant volume can be expressed as the derivative of the specific internal energy with respect to temperature. Similarly, the specific heat at constant pressure can be expressed as the derivative of the specific enthalpy with respect to temperature. It has been shown experimentally and mathematically that for ideal gases, the internal energy and enthalpy are functions of temperature only. Therefore, for a given temperature, the specific internal energy, the specific enthalpy, and the specific heats of an ideal gas have fixed values regardless of the volume and pressure. So the partial derivatives in these expressions can be replaced by ordinary derivatives. These equations can now be separated and integrated from one state to another. The integrals on the left side simply become the change in the specific internal energy and the change in the specific enthalpy during the process. These equations provide relationships between the specific internal energy and the specific enthalpy, which are properties that cannot be measured, and the specific heats and temperatures, which are properties that can be measured. In order to perform the integrals on the right side, we need to have a functional relationship between the specific heats and the temperature. In other words, we need to know how the specific heats change as the temperature changes during the process. It is a common approximation to assume that the specific heats do not change with temperature. The constant specific heat can therefore come out of the integral, and the change in specific internal energy during a process simply becomes the specific heat at constant volume times the change in temperature of the ideal gas during the process. Similarly, the change in specific enthalpy during a process is the specific heat at constant pressure times the change in temperature of the ideal gas during the process. If you approximate the specific heats as constant during a process, it is best to use average specific heat values at the initial and final temperatures of the ideal gas. In addition to these property relationships, the specific internal energy and the specific enthalpy of some ideal gases can be found in property tables as functions of the temperature.